All right, we're going to solve problem 2.28. And this is what this problem asks. Use equation 29, which is the equation I have written out, to calculate the potential inside a uniformly charged solid sphere of radius capital R and total charge Q. Compare your answer to problem 21. Let's draw out the sphere. Draw out the sphere. Okay. Here's z-axis. Here is x, y, sphere, solid, and has total charge Q. It has, this is calling my origin, radius capital R. Okay, so we need to define three things before we can do this integral. Script R magnitude, d tau prime, and the charge density, rho. Charge density, because we're told in the problem that we have a uniformly charged solid sphere, the charge density is simply the total charge over the total volume, right? And again, we can write this way because we have a uniformly charged solid sphere. Because it's uniformly charged, the charge density is just the total charge over the total volume. And we have a volume charge. That's why we have rho here. Okay. So now what we're going to do is solve for script R magnitude. Say I've got my little infinitesimal charge element dq here. And we want to find its potential at a point along the z-axis. Its vector is r. Its vector is r prime. By definition, its vector is script r. And one really cool about defining the point at which we want to find our potential on the z-axis is that it follows, because of its definition, that this angle between the vectors r and r prime is actually just the polar angle theta in spherical coordinates, because that is the definition of the polar angle in spherical coordinates, is measured with respect to the z-axis. And we'll call it theta prime, and the prime is just because it's in reference to the source charge. That's the notation that Griffith uses when referring to charges. He used these primed variables, just like we have r prime here for dq. Okay, now here's what we're going to do. We're going to use the law of cosines to find script R magnitude. So let's write this out. One quick adjustment to make here is that because R is just 0, 0, z, its magnitude is just z. So we can write script R magnitude as the square root of z squared plus r prime squared minus 2z r prime cosine theta prime. Nice. Cool. Okay. So now what we need to do is define d tau prime. And I'm saying that because I'm going to write d tau prime a little differently than it usually is written. I'm going to put the d theta prime here, dr prime, then d phi prime. And the reason I'm doing this is because I'm going to take the integral over theta prime first. And the reason we're doing that is because when we do that, we can make a nice u substitution that makes the integral a whole lot simpler. It's a kind of an ugly nightmare when you take the integral over r prime first. So to make life easier for ourselves, which is always nice, we're going to use we're going to take the integral over theta prime first. Okay, let's find our potential inside this uniformly charged solid sphere. So this equation, I'm going to take charge density out of the integral because it's constant. bring in d tau prime. I'm going to write it like this because I want to signify that we're taking the integral over theta prime first. Almost done. dr prime, d phi prime. Okay, so this is the integral over theta prime. So I'm going to take this integral separately and then substitute it back into the problem because it's just a lot easier to visualize that way. Okay, so like I promised, there's a really nice u substitution we can make here. If we let u equal to this business, du is simply 2z r prime sine theta prime d theta prime. Now, now we can rewrite this and can say that sine theta prime d theta prime is equal to du over 2z r prime. So nice. We can nicely substitute. Okay, so let's rewrite this. And before I do, let's define the limits of integration. So when theta is equal to pi, u is equal to, so this will be the upper bound of integration, upper limit. And this actually can just be rewritten as q. Theta is equal to 0. It's the lower bound of integration. U is equal to, and my bad for saying theta, it's theta prime. When theta prime equals pi, when theta prime equals 0. U is equal to and this is just z minus r prime squared. All right, so let's rewrite this integral and solve it. I'm going to take r prime squared out of the integral because it's constant. It doesn't depend on theta prime, so we can take it out of the integral. And now I just replace this with, my bad, I need to write this in terms of u. This is the proper way because did a u substitution. So we have to use these new limits of integration. I'm also going to take this 2z r prime out of the integral. Same thing, it's not theta prime dependent. And it doesn't depend on u either. We could just take it out. So then I have u to the minus 1/2 du. And this is clearly equal to and then we have the square root of z plus r prime quantity squared minus square root of z minus r prime quantity squared. Nice. Okay, so I'm going to factor out this 2 and simplify a little bit. So then I have r prime over z times this business. Cool. Let's plug this back in. Potential. Rho over 4 pi epsilon naught. Okay, so here's where things get a little tricky, and I'll explain why in a second. Okay, so I'm just going to take this and kind of do the same thing that I did with theta prime integral. Write this out. So the reason I say that this can be a little tricky is because we have two cases here, really, for this term that I'm going to underline right now. For this term, we have two cases. Because r is being varied, it's what the r prime, sorry, because we're integrating over r prime is going to change. Now, this should always give us a positive value, because when you take the square root of something, you always get a positive value. So we can rewrite this term like so, absolute value. Always going to get a positive value. Now, if z is larger than r prime, this can simply just be written as z minus r prime. You know, we can take the absolute value sign off because it's going to be a positive number. We're good. And actually, I wrote this wrong. This should be r prime is less than z, because we really care about r prime. That's what we're doing the integral over. That's the thing that's changing here. If r prime is greater than z, this is written like this, and I'll explain why in a second. Give a nice numerical example. So this is a positive, and this is consistent with the definition of square root, because square root must give us a positive term. And if to show you why this is valid, I'll show you what you're doing. If you took the absolute value of 2 minus 3, this is a similar example, because this is something negative, right? Same thing here. We all know that this is 1, but you can, and you do write this is what you're doing. You're taking minus 1 times 2 minus 3, which is equal to 1. It's the same thing. It's analogous to what I did up here. That's my justification. So I actually have to break up this integral because it's almost like we have a piecewise function here. So my first integral for this case is going to go from r prime equals 0 to z, right? That's when r prime is less than z. So then we have r prime over z times, sorry, I forgot a little squared there, but I caught it. So z plus r prime minus z minus r prime dr prime plus, second condition, r goes from z to capital R. This is when r prime is bigger than z. R prime over z, z plus r prime minus r prime minus z, r prime, and that is equal to, let's do this algebra really quick. This would be r prime over z times 2r prime dr prime plus And this integral goes from prime equals z to capital R prime over z times 2z dr prime, which gives me the integral of 2 r prime cubed over 3z going from 0 to z plus the integral of r prime squared going from z to r, and this is equal to 2/3 z squared plus r squared minus z squared, which is simply r squared minus 1/3 z squared. Cool. Now, to save some time, when we take the integral over phi prime, I could factor all this out of that integral, and we're just going to get 2 pi. So v, should really write it v of z because it's a function of z, is equal to rho over 4 pi epsilon naught times 2 pi, and then multiplied by this business we have right here. All right, so now this is also equal to, I'm going to rewrite this and include what rho is. We can write rho as 3q over 4 pi big R cubed times 2 pi over 4 pi epsilon naught r squared minus 1/3 z squared. And let's cancel these pi's. Let's cancel this. We have a 2 on the bottom. So we simplify 3q over 8 pi epsilon naught r cubed times r squared minus 1/3 z squared. Now I'm going to do some factoring to get this to look like the way the book has it. So this is going to be 3q over 8 pi epsilon naught. I'm going to factor out r squared, so that just gives us 1 r on the bottom. And then I'd have 1 minus z squared over 3 big R squared. And now I'm going to factor out 1/3. That'll give me q over 8 pi epsilon 0 capital R. And then here I'll have 3 minus z squared over r squared. Now what we really wanted at the beginning is v of r. And we remember that z is equal to r, so we can rewrite that like so. And this is exactly what problem 21 gives us. And problem 21 uses the equation to get the same result, and you can see that they're both consistent, so everything's all good. That's it for me. Thank you.